All right, I think we'll get started. So welcome everyone. Thank you for joining our roadmap launch webinar today. This is the first of two webinars where we will be presenting the low carbon thermal energy roadmap. I'm joined today by GEI, who will introduce themselves in a few minutes. But we would like to share the findings with you today, as well as AII's call to action and what AII will be doing on this topic. As the presentation goes on, please do put your questions into the chat. Once GEI has done kind of their technical presentation, we will pause for 15 minutes of Q&A, and then we will go through the questions you've put in, after which I, myself, AII, will present kind of the call to action and next steps on this report, and there will also be some time for Q&A at the end there. This webinar will probably take an hour and 15 minutes. So yeah, we're very excited to present to you today. Ali or Cecilia, if you could bring up the slide deck, please. Great, so I think we can already go ahead to the next slide. I won't dwell on this. I think probably most people joining the webinar today will have an idea of the level of impact that the textile sector has globally on emissions. The key focus of today's webinars is how heat contributes to that, being one of the key emission sources and a difficult one to decarbonize. And we're excited to tell you today about our recommendation for how to do that. So if we go to the next slide, AII therefore commissioned a report which we've titled the Low Carbon Thermal Energy Roadmap for the Textile Industry, to really answer the question of how do we transition to low carbon thermal energy? When do we do it? With which technologies? And we've studied that in China, India, Vietnam, Bangladesh, and Indonesia as some of the top textile producing countries, and namely the focus countries that AII works in as well. And we've commissioned this report not only for the sector to, align on and to drive action on this topic, but also to inform AII's grant making, AII's work on how to support the sector on its way to this transition as well. So with that, I will hand it over to the GEI team, who are the authors of this report, to take us through the first part of this webinar.
Thank you, Pauline. Well, hello, everyone. I'm Ali Hassanbegi with the Global Efficiency Intelligence. Very quick about us. We are a consulting firm based in the US doing work on industrial decarbonization across different industries and across many different countries. Fun fact, I have actually a textile engineering background. I always say that because not many people working in industrial decarbonization have textile engineering background. I did my undergrad and master's degree in textile technology engineering. And then since my PhD around 20 years ago, I kind of branched out to a broader industrial decarbonization work, doing work on other sectors as well. But having that textile engineering background and mixing that with the industrial decarbonization work that I've been doing in the past 20 years, we have been doing a number of work on decarbonizing the textile industry, including this latest work that we just published today on low carbon thermal energy roadmap for the textile industry. First, I would like to thank Apparel Impact Institute for their leadership in this area and also supporting this work. We are literally pioneering this topic for this sector. I hope you will feel the same way and you find the information helpful. So we published a report. It's actually the second report of a two-report series. We published the first report a few months ago, which was also extensive analysis of low carbon thermal energy technologies for textile industry, a lot of qualitative analysis assessing the application of these technologies across many different countries. And in this report is extensive quantitative analysis and then discussion on the roadmap and the recommendations, which we published today. It's 100+ pages report, and we will do our best within the short period of time we have to kind of give you a good snapshot, but certainly go to the report for much more detail and results for the 5 countries that we have studied: China, India, Indonesia, Vietnam, and Bangladesh. And with me today also is my co-author, Cecilia. Cecilia, would you like to introduce yourself?
Sure. Hi, everybody. I'm Cecilia Springer. I'm a principal at Global Efficiency Intelligence, working on a wide range of industrial decarbonization topics and research with a big focus on electrification.
Thanks, Cecilia. So let's get into it. So we are going to give you some introduction, brief also information about the approach. We have again discussed it in detail in the report. Then we'll show you the result of our study focusing on the low carbon technologies for heating in textile industry, namely for steam generation and also for thermal oil boilers or hot oil boilers. And then we will conclude with the roadmap that we have put together and a decision tree for textile facilities, how to select these technologies, the kind of thought process you need to go through, and some recommendation. We will have Q&A, so please put your questions in the Q&A box. We will have 15 minutes, and then we will conclude with AII presenting their call to actions and what they're doing to take this to the next level. So we are Global Efficiency Intelligence. We also launched Textile Sustainability Hub more than 6 years ago. It's a platform that we share all the work that we are doing in this space in textile industry decarbonization there. And also, if you're interested in the topic of industrial electrification, we have a whole website, Industrial Electrification Center. We share a lot of information there on this topic. So please check those websites if you're interested. So as I mentioned, this is the second report of the series. So a few months ago, we published the first report, extensive analysis, 75 plus pages, where we looked at the six different low carbon thermal energy technologies and discussed them and explained them, and also assess the readiness for these different technologies in different countries. Top 20 textile producing countries, and we kind of show in different format how different countries are ready or not ready for adopting these technologies. So I refer you to that previous report for more information. So, so when we talk about the industry, and in this case, textile industry, there is electricity use and there is fuel use for heating. Electricity is kind of straightforward. You need to use the renewable. Fortunately, more and more in major textile producing countries, for example, India, China, and now Vietnam and other countries, we are getting more renewable generation. We are getting corporate RE procurement. So that is becoming kind of relatively easier now to decarbonize, the electricity part. The heating is the challenge. That's where everybody is scratching their head. So that's the focus of this study and today's conversation and the report, how to decarbonize heat, which accounts for a significant portion of the emissions in industry, but also textile industry. So just for a second, let's step back, the big picture. Almost everything you do to decarbonize industry, any industry, including textile industry, falls under 5 decarbonization levers or pillars. Material efficiency, circular economy, anything you talk about recycling, waste management, waste reduction, demand side work, that's that pillar. And then energy efficiency is straightforward. Electrification of heating, which is a lot of talk today we are going to give on that topic. Low carbon fuel and feedstock, for example, solar thermal, sustainable biomass, etc. And then, of course, CCUS, but for textile industry, that is kind of irrelevant, CCUS, carbon capture sequestration. So this report we published today and the webinar today focuses on 2 pillars, electrification of heating and low carbon fuel. Namely, we have included biomass, sustainable biomass, of course, would be desired. And also we included natural gas. It's not really low carbon fuel. It could be lower than coal, but we will talk about some of the caveats as well. Again, in the previous report we published a few months ago, report number 1, we did extensive analysis of these different low carbon fuels and heating technologies. And we compared them in a matrix with regards to certain criteria. Don't try to read this. Again, this is from previous reports, so I don't want to spend too much time on it. But basically, the more dark blue you see for any technology, that's a good thing. And if you just look at this, I think in an instant, you will see that electrification technology, namely electric boiler, industrial heat pumps, they have more dark blue, more optimal with regards to, energy saving, CO2 emission reduction, OpEx, etc. Of course, none of the technologies are perfect. So basically, they came as the kind of winning technologies, both medium-term and long-term, with regards to advantages they can provide. Of course, there are applications for sustainable biomass that in near term could provide a solution, and we will talk about that. And also natural gas is an option, but many of the top textile producing countries actually do not have domestic natural gas. They have to import it, all the issue with the import infrastructure, volatility of the cost, etc. But again, I refer you to the first report, but just to show you that the technologies we are discussing today are extensively also discussed in the previous report. And in today's webinar, we focus on the techno-economics of these technologies: electrification, electric boiler, industrial heat pump, biomass, and natural gas. And I hand it now to my colleague Cecilia to talk on a few slides. Cecilia?
Great, thanks, Ali. So to continue, I'll share some more about our study scope and our methodological approach to the techno-economic analysis. As Ali mentioned, we are analyzing 4 low-carbon thermal energy options. 2 of them are electrification technologies, the electric boilers and heat pumps, and 2 of them are alternative fuels, biomass and natural gas. And in terms of geographic scope, we looked at 5 countries, as Pauline mentioned. These are some of the top textile producing countries by their export value, as well as domestically their value added in manufacturing. So we looked at China, India, Vietnam, Bangladesh, and Indonesia. And importantly, we looked at heating for both steam production as well as thermal oil-based heating. And this is important because combined, they represent the majority of fuel use in a typical textile wet processing plant, with steam generation accounting for about 50 to 60% of this fuel use, and thermal oil heating is not insignificant. It can be 30 or even 40% of fuel use. So note that throughout our presentation, we're talking about these 2 heating mediums. Next slide, please. So in terms of our approach and methodology for this study, we did a techno-economic analysis of heating-related energy use. We also looked at emissions and costs at a typical textile wet processing facility in each of these 5 countries. So we developed a model to represent a typical facility with annual production of 8,000 tons of fabric per year. And so we're not modeling a real facility, but we're using all of our data on wet processing and typical production processes, their energy needs, and so on, to look at a typical plant and what it would look like in each country. We added country-specific data on fuel and electricity prices, grid emissions factors, and other things that are specific to the 5 countries that we analyzed. We also developed 2 scenarios, or what we call pathways, for the electricity supply. This is very important for our analysis of the electrification technologies, is understanding where the electricity comes from. And so we looked at 2 electricity supply pathways, one with less renewable energy procurement and one with relatively more renewable energy procurement. And we called this the baseline grid plus renewable energy procurement pathway, and then the ambitious grid plus renewable energy procurement pathway. And so these vary depending on how much renewable electricity a facility, the typical facility that we're modeling, could procure. And the reason this is important is because procured renewable electricity is lower carbon, 0 carbon compared to grid electricity. And what we found is also that procured renewable electricity now and in the future can be procured at a more favorable rate relative to grid electricity. So this has big implications for the emissions and cost impacts of electrification. And so the figure on the right shows the decarbonization pathways for the electricity supply based on the baseline or the ambitious scenario. And these vary by country based on their own projected decarbonization pathways, as well as the amount of renewable electricity they can procure. Next slide, please. And so how did we determine what a typical textile facility might be able to procure in terms of renewable electricity for the baseline and the ambitious pathways? So for each country, we did an assessment of their energy systems landscape, and I encourage you to go to the report to see all of this, useful context and sources about each country. We looked at the alternative fuel availability for natural gas and biomass in each country, the state of their electricity grid, and then also their corporate renewable electricity procurement markets. And based on the state of the development of these RE procurement markets, we use this to inform our scenario development. And so you can see that there's variation across the countries that we studied, with China, India, and Vietnam having relatively robust markets for corporate renewable electricity procurement now and projected to be so in the future, whereas Indonesia and Bangladesh, those markets are still emerging. And so there is country-specific variation across our scenarios in terms of how much electricity supply a typical facility could get from the grid versus procuring it, for example, through power purchase agreements. Next slide, please. So next, we'll move into our results from this analysis, from our techno-economic analysis. And I will present about our alternative fuel results and then turn it over to Ali to discuss electrification. The first thing that we did, we looked at the annual energy use, annual CO2 emissions, and energy costs of the conventional versus the alternative fuel technologies. In most of the countries studied, in all of them except for Bangladesh, the reference technology or the conventional technology is a coal boiler. For Bangladesh, the reference technology is natural gas, because that's the dominant fuel used for heating in the textile industry there. And so for biomass and natural gas relative to coal boilers is what's shown here. We looked at biomass, both sustainable sources that are assumed to be carbon neutral based on their uptake of carbon in the life cycle of that biomass. And then we also looked at an unsustainable biomass. This is based on the IPCC emissions factor for direct combustion of biomass. When you burn it, it can actually be more emissions intensive than coal. And so on the top left, you can see that in terms of annual CO2 emissions, that unsustainable biomass sources could actually have higher emissions than coal-fired boilers. And so sustainable sourcing from waste sources like agricultural residues is essential for the goal of emissions reductions. For natural gas, what we found is that switching to natural gas boilers could decrease emissions from a direct combustion emission standpoint, because natural gas has lower emissions intensity than coal. However, if you take into account methane leakage, which is a very potent greenhouse gas that comes from the production process of natural gas, this could actually negate the emissions benefits of natural gas. And of course, methane-related emissions are outside of the scope of something that an individual textile facility can control. It happens upstream during exploration and extraction, but it's very important, just like biomass, when considering the life cycle impacts of these alternative fuels. So there are significant caveats to the use of these fuels as decarbonization technologies. Next slide, please. So for all of the technologies that we evaluated, we also looked at their energy costs, and we compared the conventional technologies and then the alternative fuels or electrification technologies in terms of the energy cost per kilogram of fabric. And our energy costs take into account fuel and electricity costs per kilogram of fabric. And we also looked at carbon pricing. So for this study, we assumed that there would be carbon pricing Across the countries studied, for example, China already has a national emissions trading system that could expand to include the textile sector in the future, or carbon pricing from a carbon border adjustment mechanism, which is a growing policy in use in the EU and potentially in other major textile importing countries in the future. So you'll see that throughout our analysis. So what did we find for energy costs for biomass and natural gas? Here we present the example for China, but please refer to our report for extended results on all countries. For biomass, we know that right now, lower prices for biomass are driving significant biomass adoption in a lot of textile producing countries. However, it's very important to note that overall biomass supply, sustainable biomass supply, will be limited if multiple facilities across the textile industry are adopting them. There's just not enough supply, and that will drive prices up in the future. So we emphasize that for biomass, it's a niche solution for some locations that could have abundant biomass supply in the near term. For natural gas, the graph on the bottom left, we find that in China, as well as across all countries studied, natural gas is typically more expensive than coal. And that's because the countries that we studied are typically reliant on imports for a large portion of their natural gas supply. And natural gas imports are also not necessarily going to be prioritized for the textile sector. There will be other applications in, for example, the electric power sector that could get limited supply first. So prices for natural gas could be volatile based on global market dynamics, and they will likely rise, which limits the financial attractiveness of natural gas as an alternative fuel. So I'll note that we also present results. These are for steam boilers, and we also present results for thermal oil boilers for all of these technologies in the report, but they're not shown in our slides due to lack of time. So I'll turn it to Ali for any final thoughts on alternative fuels and then moving towards our results on electrification.
Thanks, Cecilia. I think you already explained it clearly. Just one note on carbon price, we assume very, very low conservative carbon price, but if you don't like it, you can just ignore that gray part. And biomass also, we are going to talk more about this, but basically, if it's not sustainable, it's worse than coal. That's the takeaway. If there's one fuel that's worse than coal, is unsustainable biomass. It's literally emitting more emission than coal per gigajoule. And then all the biodiversity, ecological, and all the other issues that associated with unsustainable biomass. Also, agricultural waste, they are not by default sustainable. Just imagine, for example, palm shell from palm oil. Like if you use palm shell, it's not automatically sustainable. I mean, we know all the true stories about, deforestation in Southeast Asia from palm plantation. That's all happening because of money and profit. And imagine you go and pay them more money for the waste that you're generating. What kind of incentive you are providing? So agricultural waste, they are not automatically sustainable, but there are definitely cases that they can be certified as sustainable. But you have to be very, very careful with biomass and make sure it's verifiably sustainable. Otherwise, it is worse than coal. So on electrification, again, we have a lot of detail in the report, but very quick snapshot. We looked at electric boiler and heat pump. Here we are showing the energy use for electric boiler and heat pump, annual energy use for this typical wet processing plant. By the way, for those of you who are not textile engineers, typical wet processing plant is a textile plant that does the pre-treatment, dyeing, maybe printing and finishing of a fabric. That is, and that's very fuel heat intensive in a textile sector. And so if you want to decarbonize heat, that's the place you want to start. So that's what we mean by typical wet processing plant. So this results showing the annual energy use for a coal-fired steam boiler on the left, and then electric steam boiler. Coal-fired steam boiler, typical efficiency, 70 to 80%. Electric steam boiler, typical efficiency, 98 to 99%. So immediately you get around 20% efficiency gain in final energy term. Heat pump, they are extremely efficient, way more efficient. So here, when we talk about heat pump, we are talking about a steam generating heat pump. So keep that in mind. So a steam generating heat pump that are applicable for textile industry, they usually have coefficient of performance, or COP. That's the indicator we are assessing their efficiency with. COP of more than around 2 to 2.5. In simple terms, that's more than 200% efficiency, comparing to electric boiler of 99% efficiency, comparing to the fossil fuel combustion boiler of like 70 to 80%. So heat pump they're very efficient. That's why you see the significant drop in annual energy demand of a steam generating heat pump versus coal boiler. How does it translate into emissions? So again, there is a lot here. You don't need to read everything. I'll try to kind of tell you the takeaway. So the graph on the top left shows the electric boiler annual CO2 emission compared to the coal-fired boiler. The red lines, they are the fuel CO2 emission from fuel used in the coal boilers. And then the ones next to it are for the electric boilers in 2030, 2035, 2040 in kilogram CO2 per year. So for the electric boiler, we have two scenarios, and also for heat pump. One scenario is for the baseline grid plus RE procurement. The other one, ambitious RE procurement. Of course, if these are the results for China, like in 2030, we assume in the baseline scenario, China like gets 50% of electricity. This textile plant in China gets 50% from the grid, 50% from the RE procurement. You can see the emissions implications. Like even in 2030, with that assumption, with electric boiler in China, you have electric boiler using half of electricity from the grid and half from RE, having significantly lower emission than coal boiler. And of course, the other scenario, we assume you can get 100% RE in 2030, which by the way, you can get it today. If you go to China, India, plants significantly larger than textile plants, like steel plants that are doing PPA in India, significantly larger plants doing PPA, power purchase agreement in China. So it's doable even today to get 100% RE in a textile plant if you electrify. I'm not talking about the cost in terms of availability in some of these countries. And if we go to 2035, 2040, as Cecilia explained, of course, the emissions of the electricity under both scenarios drops. And when you see no lines, that's because already 100% RE is used. So basically zero emission. You can get to zero emission in 2030 in China, in India, in Vietnam, based on our analysis. And if you ask me, you can get to zero emission even tomorrow in China, India, and Vietnam, where the corporate RE procurement infrastructure is in place. Same story with heat pump. It's just heat pumps are significantly more efficient, as I just mentioned. So you just see that the emissions drop and the delta of emissions between heat pump and coal boiler is significantly larger because they give you substantially more efficiency, so substantial lower emission associated with that, with heat pumps. So heat pumps definitely are a significant advantage here when we talk about energy and emissions. Cost. So similar to what Cecilia presented, we did the cost analysis, energy cost. So we compared the energy cost of electric boiler and heat pump. Energy costs are presented in dollar per kilogram of fabric produced. So the first line and 2030, 2035, 2040. Let's just look at 2030 for now in the top left, electric boiler. The first line is for coal boilers. The red part is fuel costs. The orange part is the electricity cost, and then the small gray is the CO2 cost. So, of course, the coal boiler, a significant portion of the cost, energy cost is fuel cost. Next to it is the electric boiler with the baseline RE procurement. You can see the energy cost is basically almost double. With electric boiler with ambitious RE procurement, assuming more RE, which assumes lower cost of RE compared to the grid electricity, you can see has lower cost of energy, but it's still kind of substantially higher than coal. But as you move to 2035 and onward, you can see the gap close because we are using more RE with a bit lower cost than the grid electricity. But overall, that's one of the barriers for electric boilers. Electric boilers, the efficiency gain they give you is 20%, which is good, but it's still because electricity price is more expensive per unit of energy compared to fossil fuel in most of these countries. Here we are presenting China result, by the way. So you can see that delta of the gap of the energy cost. By the way, here y-axis, the unit is dollar per kilogram of fabric. So even though it doubles the energy cost, but look at the number. Coal boiler, it costs around $0.25 per kilogram of fabric of energy cost. With electric boiler, in the expensive case scenario, is around 4.5. So the delta is around basically 20 cents per kilogram of fabric. A t-shirt is lighter than a kilogram of fabric, or it's a kilogram of fabric. So we are talking about 20 cents per piece of many types of cloth. So keep that in mind. It I think gives a different perspective. However, when we go to the lower part, heat pump, again, because of the significant efficiency gain that they provide, they help with lowering the cost of energy because they're using significantly lower amounts of energy. So immediately, even in 2030, the energy costs of heat pumps are lower than the coal boiler. So that's another advantage that heat pump efficiency gives us. So that's only energy costs, but people say, okay, how about capital costs, other costs? So we calculated what we could say levelized cost of heating. Basically what we did, we got the life cycle of the technology, let's say 20 years, and we included all the CapEx and OpEx and energy costs and even carbon cost. And then we calculated dollar per megawatt of heat, thermal heat, that each of these technology provide. The first bar, these are the results for China and India. Let's look at China. The first one is coal boiler, next to it natural gas, and then sustainable biomass, unsustainable biomass, and then 2 bar for electric boiler for different electricity supply scenario, and 2 bars for heat pump. What's the takeaway? Across, I think, all countries, heat pump, despite the fact that they have the highest capital cost is the orange part. If you look at the heat pump, you can see a big orange part here, capital cost for all the countries, because heat pumps are expensive. But because of the significant efficiency they provide over the lifetime of the technology, you would be saving substantial amount of money because you can see like the life cycle cost, the levelized cost of heating for heat pumps substantially lower than coal or natural gas or any other technology. So one takeaway you should have, you cannot judge these technologies, especially things like heat pump with like payback period. You cannot get to net zero with 2-year payback period, especially now. 10 years from now, when the cost of a lot of things drop, the CapEx drops, the RE drops, then maybe. But now there are different ways of looking at costs. Levelized cost is a good way to look at it, and even energy cost, and looking at the gap, the magnitude of the gap, and what it means for the green premium. But as you can see across all countries, heat pump, they have the lowest levelized cost of heating. And electric boilers, actually, in most countries also, they have lower levelized costs compared to the coal boiler. So that's another takeaway to have on the cost side. We did the same analysis for thermal oil boilers. As Cecilia mentioned, thermal oil boilers, they are used extensively in the wet processing plant, mainly to provide the thermal oil that goes into the stenter for the heat setting of the fabric. I don't get into too much detail of that. And they usually actually accounts for 30 to 40%, sometimes higher based on the data we have got, of the fuel used in a typical wet processing plant. But it's just a boiler. It's just instead of, boiling water, it heats thermal oil and it goes into a closed loop and provide the heat. You can electrify. Electric thermal oil boilers, they have been around for decades. So we did the same analysis. They provide, efficiency, so lower energy use for sure. The CO2 emission, annual CO2 emission, depending on the scenarios you look, it's always lower than coal boilers. I go through it a bit quickly. I'm trying to be mindful of time. So people always ask, okay, if we electrify, there's going to be electricity demand. So how about that? So we are showing that what would be the additional electrical load if you electrify? For the graph here shows the additional electrical load if this typical wet processing plant that produces 8,000 tons per year of fabric, finished fabric, electrifies. For electric boilers, we are looking at a bit higher than 8 megawatt of new load. For heat pump, because again, significant saving it provides, it requires much less electricity. Therefore, a bit higher than 3 megawatt. So less than half of electricity load. And hot oil boiler, electric hot oil boilers, they require around 7 megawatt. These are, by the way, are not big numbers. These are fairly small numbers. We do work in other sectors. These are really tiny numbers when we talk about renewable electricity supply needed. So it's quite doable to electrify and get 100% even RE to supply this. So to wrap up, I think I already talked about these items. Basically, electrified technologies, they provide significant efficiency. As you saw, in all cases, they reduce the emissions, even in near term, depending on the electricity supply mix. But heat pumps, they have the most advantage here. They can give you the reduction immediately. They can give you even cost saving. And they're commercial technologies. This is the good news. Everything we are talking here today, they're commercial technologies. They're not like some future technology. You can buy them today. But electrification goes hand in hand with renewable energy procurement and supply. At the end of the day, even though you get emission reduction with some mix of RE compared to coal, we are in the age of net zero. Eventually, we want to get to net zero. Not tomorrow, but at some years, definitely by 2050. So we need to clean up the electricity. And we need mechanism, regulatory infrastructure for corporations to procure RE. Fortunately, some of the major textile producing countries, India, namely China, and now Vietnam, they are some of the best in Asia in terms of corporate RE procurement. India is one of the best in the world, honestly. So that's a good news. And we have a lot of textile companies there. So there, it's a sweet spot for electrification. But countries like Indonesia, like Bangladesh, they are lagging behind, mainly because not only generation, but also not having the regulatory infrastructure for corporations to go procure RE. So we need that to happen. In summary, natural gas basically is not a solution. It's a fossil fuel. It's nothing nice for actually, we should call it fossil gas. Most textile producing countries, if you look at our first report, they simply don't have it. They're all importing it. We saw what happened in the past few years. The price fluctuating, it's just going to increase. And if LNG is imported, more additional emissions associated with that. So it's basically not a solution. And if you add the methane emission to it, you're not really reducing emission. Biomass can be a near-term solution if, and that's a big if, it's sourced from sustainable sources, which is limited. And many industries and power sector are going to compete for this limited source, and the prices will go up. And if you find cheap, easy biomass, there's a good chance it's just simply not sustainable. If it's too good to be true, that's probably the case. And firsthand, we have seen in a number of countries in South Asia and Southeast Asia, a substantial amount of non-sustainable biomass is used. It's basically a matter of time. Some of the NGOs knock their doors, textile plants, apparel brands to get into trouble with that if they're ignoring the environmental consequences. Electrification basically is the most viable, I would say not even long-term, short-term solution in some of the countries and medium to long-term in some others. The technology is there, it's commercial, and the renewable generation is there. It's just a matter of the cost and financing. So I would say textile industry is easy to decarbonize sector. We do work in other sectors like cement and steel. They're called hard to abate. Textile is easy to abate because the technologies are here. It's just we need to figure out financing and the cost, and the stakeholder need to work together on that. So I'm going to hand it over to Cecilia to walk you through the roadmap and recommendations. Cecilia?
Great, thank you, Ali. So for the last part of our presentation, I'll be sharing the roadmap part of this report. So we provide several different aspects to this roadmap, starting with implementation guidelines for electrification, shown here. The other technologies evaluated in the study, namely biomass and natural gas boilers, they're already widely adopted, so we didn't provide implementation guidance. But because electrification is, we would say commercial, but newly commercial, we also thought it would be an important resource to start providing some guidelines. So in the report, we walk through some of the steps that a textile facility could take to prepare for electrification, from data gathering to planning for the electrical load increase and the types of analysis a facility would need to do and the equipment they might need. We also walk through what a feasibility assessment for electrification technologies would look like. And to that end, separately from this project and with support from the Outdoor Industry Association, GEI recently released a textile heating electrification tool. And I'll try to share the link in the chat, which we think can be a first step towards understanding feasibility of electrification for textile facilities, where you can use it and put in your own data. And we also discuss a little bit about implementation. So these are some guidelines that the report provides for facilities that might be looking at next steps. Next slide, please. As part of the roadmap, we also discuss the financing mechanisms that can be available for transitioning to low carbon heating. And to that end, I want to highlight that AII last fall published the brand playbook for financing decarbonization, which is oriented towards brands and different financial tools that can be available. But of course, it can also benefit textile manufacturers and even financial institutions. And so we draw from that in the report, and here highlight 5 different financial strategies for advancing low carbon heating in the textile industry, from traditional debt-based financing to emerging green financing mechanisms like sustainability-linked loans and guarantees for green technologies based on sustainability performance metrics. I think also a growing area is government, development finance, and philanthropy support for low carbon heating as awareness of its decarbonization potential grows across institutions that are active in the countries that we mentioned, for example, the World Bank, Asian Development Bank, Green Climate Fund, and so on. There's also venture capital equity-based investments and brand premiums, which will be very important, I think, in the early stages, and we discuss this more in the recommendations. So we draw these different mechanisms together, and we also assess country-specific mechanisms that may be available in each of the 5 countries. And of course, these will need to be done in combination. There's no one silver bullet. Next slide, please. So as Ali previewed before, we also developed a decision tree for textile facilities looking to adopt low carbon thermal and energy technologies. And of course, it's a simplification, and there are going to be facility level considerations, but we think it is an important high level guide for decision making as a first step. So I'll start walking through this, which we think is important to go through. We think the very first step, and you've certainly seen this from the results of our analysis, is that facilities need to evaluate their corporate renewable electricity procurement feasibility. Are they going to be able to procure renewable energy by 2030, which is the timeline of our analysis, and also it'll take a few years to get electrification technologies in place. Renewable energy, of course, is a key enabler of electrification and decarbonization. And if it's available, then you'll move through the decision tree to assess the feasibility of electrification technologies. And so the choice between the electric boilers and the heat pumps depends on factors like the electricity to fuel price ratio. And for heat pumps, if the facility can access upfront capital. We know that heat pumps do have significant investment costs, and so that's a key decision-making factor. But if they do, then all signs point to heat pumps, as we've showed in our analysis. As for electric boilers, it's important to note that there is a threshold in terms of the emissions factor of the electricity supply, above which they could increase CO2 emissions in the near term. But if it's below a certain threshold, then they can decrease emissions. Another important factor for electric boilers is the so-called spark gap, or the electricity to fuel price ratio. So if there is a favorable spark gap, then there are cases where electric boilers could be a good solution. However, that is not the spark gap that you would necessarily see in these countries today. for the most part, you can see that heat pumps will be a preferred solution because they are so efficient that they don't need a highly favorable electricity to fuel price ratio. And they can also deliver emissions reductions even below a very significant, a very high grid emissions factor, actually higher than the countries that we've analyzed, especially as grids decarbonize over time. However, if corporate renewable energy procurement is not feasible and the grid emissions factor is too high, there's no capital, then the decision tree will move you towards sustainable biomass. And there are several steps to be considered in terms of, is there uninterrupted supply? What's the pricing now and in the longer term? And very importantly, can it be fully verified as a sustainable source? Can the air pollution emissions from the on-site combustion of that biomass be controlled? And so then these are the hurdles to be cleared in order to make sustainable biomass boilers the preferred outcome based on this decision tree. And we also mentioned to reevaluate when the corporate renewable energy procurement becomes feasible, since markets are moving quickly. Next slide, please.
Just a quick note. I realized there are some typos and missing links here. This is like a previous version. We corrected it in the report, but apparently it's not reflected here. Just please refer to the report for a very slightly different version with some of these typos are corrected. Sorry about that. Go ahead.
So we end with our recommendations, and in the report we have country and stakeholder specific recommendations, and here we'll just summarize our recommendations for apparel brands. And so in the near term, from now until 2030, just want to highlight the most important thing is to develop and implement pilot electrification projects just to make the case and demonstrate. It's also important to engage suppliers in reducing their thermal load as a first step and sort of solution before electrification, working on renewable energy procurement. And then for biomass, the sourcing of biomass as a near-term option, it needs to be fully verified. And in the meantime, preparing the stage for electrification. From 2030 to 2035, we recommend that's when scaling of low carbon technologies, particularly electrification, needs to happen with technical and financial support. And then by 2040, our roadmap, makes the recommendation that textile manufacturers can fully transition to electrification as the deep decarbonization long-term solution and paired with renewable energy. Next slide, please. We also break down recommendations for textile manufacturers, and these are kind of almost like a mirror image of recommendations for brands, but it's all about implementing those first few pilot electrification projects. In terms of preparation for longer term electrification, there needs to be investment planning and planning for renewable energy procurement. And then where feasible, using certified and sustainable biomass as a near-term solution. From 2030 to 2035, it's about integration of that renewable electricity, implementation of electrification, and then phasing out biomass, again, as electrification becomes the preferred decarbonization solution. And then by 2040, full transition, as I mentioned in the previous slide. And so we encourage you to reference the report for more comprehensive country-specific recommendations. And I'll turn it over to Ali for concluding remarks before our Q&A.
Thanks, Cecilia. I think we are running a little late, but basically to conclude, we need first movers. These technologies are commercial technologies. You can buy them today. There are countries, textile producing countries, namely India, China, Vietnam. They are actually the sweetest spot for adoption of these electrification technologies. So we can't just wait for this to happen and you say the price will drop with economy of scale. Economy of scale does not happen with time. Economy of scale happens with adoption. If we don't have the first movers and beyond that to adopt, nothing is going to happen. The price is not going to drop in terms of price of technology and all that. the knowledge will not be gained. So I hope we will have enough progressive brands and suppliers and textile plants, which I'm seeing actually is slowly happening. And with the help of folks like AII and others and some of the progressive brands, if we see some of these pilots and demonstration, again, this is not emerging technology pilot, it's a commercial technology. It's just happening in our sector, the textile sector. The conversation will completely change around this. It's just people will then follow because they see this is working, this is reducing emission, and economically is doable. We just need to bring the stakeholders, the brands, the suppliers, the financiers, and some grants to make these first movers kind of do this. And we cannot expect textile plants and suppliers to do this. It's just not fair to ask them to do it and pay for it. So brands need to play a role. AII, other folks who are outside also can bring help and financing and technical capability. I think it's important to make this happen between now and 2030. So with that, I would like to conclude our technical presentation and go to Q&A. I think, Pauline, you would be...
Yes.
Moderating. Sorry, we went 5 minutes, I think, over time, but we had a lot to say. Hopefully that was clear enough.
And we've got lots of questions, which I have to apologize in advance. We cannot all get to today. So definitely read the report because many of them are answered there. And just a reminder that this webinar goes longer than the hour. So aiming for 1/4 past, as after the Q&A section, I will be giving a presentation on AII's call to action and what activities AII will be undertaking to activate the roadmap. So the first question for you, Ali, which I think is a good kind of probing question with these results. So given there are, challenges, risks from a short-term perspective, if you're looking at some of these alternative fuels, namely natural gas and biomass, and seeing that electrification will be more viable from 2030, does it still make sense for suppliers to put efforts into these solutions, which, could be considered temporary? Or should they wait until electrification is viable and affordable for them in 2030 and then take action then?
That's a very good question. Actually, I was thinking to talk about it. Well, again, electrification is viable in some of these countries. If you look into it closely, I think with a little bit of support, it's really viable. It's not like in 2030 something will magically happen. But let's say in some country like Indonesia or somewhere that electrification, the RE is not there. I would say if you can, natural gas simply in many of these countries is not there and it's just too expensive. I don't know how you would justify this. And again, if you include the methane emission, which you should include, look at many neutral scientists like publish on this. So it's kind of established fact, there is methane emission. So if you just very objectively look into it, you are not really reducing emission. Then what are you doing? Switching from coal to natural gas, going through all that trouble. So that leaves biomass, which we see in Asia, a lot of people going towards that, which is a big concern because we know a good portion of it is just simply not sustainable biomass. But if you can verifiably kind of use sustainable biomass, like we know, for example, there's rice husk, there's open field burning in February in all the Southeast Asia. If it can be collected, used as fuel, I think that's very justifiable. But there's a reason it's not being collected and used and just burned in the field because it's expensive. The cheap ones, they have issues with it. But if you can verify, I think near term, sustainable biomass could be a solution. But if you have even a slight doubt on the biomass and the sustainability, I would say keep burning coal, because if there is one fuel worse than coal is unsustainable biomass. Don't take my word, just go to IPCC greenhouse gas inventory. There are 2 tables, one for the power sector, one for the manufacturing. They give you emission factor per gigajoule for all the fuels. Almost all the biomass have emission factor higher than coal. So if it's not sustainable, what are we doing? And then all the other issues related to ecosystem and biodiversity and land use change and food versus fuel and etc. So that's kind of my quick answer to that.
And maybe on that, there were a lot of questions on what sustainable biomass is. So could you provide just a quick overview?
Yeah, maybe. Do you want me to jump in and summarize from the report?
We did a 1-hour webinar on that, but Cecilia, go ahead. I think we need to refer folks to the standards and all that, but go ahead, Cecilia.
Yeah, I think actually our first report covers this in detail and the second report summarizes, but just briefly, you know, in the report, we talk about how energy crops and woody biomass are not considered sustainable biomass sources. They can contribute to deforestation and overall increased CO2 emissions. There's a lot of scientific discourse and debate about, you know, how much they take up carbon versus how much they emit upon combustion. And our first report also has tables of existing certifications and definitions. You know, definitions vary. For this report, we do state that agricultural residues are likely the most sustainable biomass source. They're byproducts of existing agricultural cultivation. So when we say sustainable biomass, we mean agricultural waste where there's no deforestation risk, and certified wood waste certified palm kernel shell sources. And that's our limited definition. And you can see how we model that as being carbon neutral. But of course, verification is needed, and the report points to some specific resources around that.
Great,
Just
thank
to
you.
add to that, in my view, if you really care about reducing emissions, not just putting something positive for publicity, if you're going to spend a couple of years of your time and all this money, it just makes sense to spending in a real solution, not just something that you yourself know is not the real solution, is just going to add to the problem or not solve any problem. So, and there is a real solution. It's not necessarily easy. It's not necessarily cheap in the beginning, but there is commercial real solution sitting there.
Great. And I think one of those real commercial solutions is heat pumps. We've had a lot of different questions on them, so I'm just going to group them because I think there's differing kind of technical understanding in the call. So could you explain a bit about how heat pumps kind of take heat from existing sources, given that that drives a lot of the efficiency? And then also answer some of the questions about, what are the kind of maximum temperatures we see today? Is this technology really kind of ready? Why do we need the pilots? And how does it actually kind of service the heat needs of our sector?
Yeah, a couple of questions there. Yeah, there are commercial. Literally in the past 2 weeks, Cecilia and I, we have been talking to, I think we talked to 3 industrial heat pump manufacturers in US and Europe. And there are more, it's just we are talking to different ones. We have been talking to them. So in textile wet processing plants, I think those folks working in textile, they know there is waste heat because we are doing all this processing. There's hot water effluent coming out. Based on all the data we collected from tens of different plants, at least in the past few years, we are getting to around 50 to 60 degree Celsius waste heat sufficient to fit into the heat pump to generate a steam. Usually we categorize into like lower temperature and slightly high temperature. 120 to 150 degree Celsius steam meets almost all the steam demand in a wet processing plant. For some of the washing and all, you need lower temperature, and then dyeing, you need a bit higher temperature. So everything we talk today is a steam generating heat pump. You can have so-called industrial heat pump that they give you like hot water, let's say 90 degree or even 100 degrees Celsius. That's not what we are interested. Why? They're not going to save you much fuel. If you get the water from, let's say, 20 degrees Celsius, and you want a steam at 120 degrees Celsius, to heat the water from 20 degrees Celsius to a water at 100 degrees Celsius, still water, it takes only around 10% of the energy, total energy. 90% of the energy is used to get the water from 100 degrees Celsius to a steam of 120 or 150 degrees Celsius, around that number. Because of course, enthalpy of evaporation, we studied in the high school. So hot water heat pump, of course, they're gonna give you some saving, but in textile wet processing, well, we need a steam generating heat pump. And if you're thinking, oh, because many textile plants, they only need hot water, like washing and other things and desizing and all that, it doesn't work that way. You cannot just make hot water and just run it through the machine. And a lot of these things are batch processes, and the solutions. You need the process to stay heated, and for that, steam is used. So therefore, we need a steam. Unless completely the processes designs are changed, which again, that would be major intrusive changes in many, many tens of hundreds of textile plants, which we are not interested. So we need a steam. We need a steam generating heat pumps. Currently, many commercial ones, they're providing this up to 170 degrees Celsius. Recently, more and more, they are claiming up to 200 degrees Celsius steam. Fortunately, in textile, all we need is around 150 degrees Celsius or less. So the current commercial steam generating heat pumps, they meet that. Yes, we know that like there are not hundreds of these suppliers, there are like tens of them, and depending on geography, you might have limitation. Europe is a great place. Many of them are there. Japan is a great place. Korea has some. In US, we are having more now. China is definitely going to pick up the speed. I talked to heat pump manufacturer in India. So, but if you go to like, I don't know, Bangladesh, Indonesia, and some of the other countries, you may not have local manufacturer, but like any other technologies that they import, they can import the heat pump, no problem. So, yeah, that's I think hopefully is a clear answer.
Great. And then I guess on the finances associated with these technologies, there's a high upfront capex. What is kind of the typical return on investment today? And when do you predict that these types of technologies can be implemented without financial support?
Yeah, but depend on the technology. Like for heat pump, for example, which is the technology of interest here. Yeah, the payback period depends on the, of course, case by cases, but we get, I think, roughly payback period of around less than 10 years, I believe. Like Cecilia, 8 to 10 years. But depends on the fuel price versus electricity price, which you know varies significantly. The price, these are based on mostly Western heat pump manufacturer. Like any other technology, we are really helpful. China is going to pick up soon on this heat pump because they are electrifying actually fairly aggressively. And we know what happens when China kind of mass adopt a technology. Usually they produce a fairly decent technology with like 1/3 or 1/4 of a price. So we expect that significantly help with the economics of heat pump. And then some sort of carbon price, whether it's the carbon border adjustment or also local carbon price, that might help. So those will help maybe post 2030 to bring this payback period and so on. But as I said earlier, you cannot get to deep decarbonization with 2-year payback period. That 2-year payback period or 3-year payback period, this is a standard practice in industry. That is for minor or retrofits, energy efficiency. Here we are talking about net zero. We are talking about deep decarbonization. So we need a little change of thinking here. That's why we presented the life cycle cost or levelized cost of heat. So I think we need to think a bit differently about costs as well. But yes, at this moment, in any other sector we are studying, initially there will be some sort of a green premium, but hopefully that will be reduced.
Great, thank you. And then maybe to take a couple of the other questions, just to summarize, we've been talking a lot about electrification, but when we look at countries like Bangladesh and Indonesia, which have slightly kind of longer timelines for that, what is the recommendation of action there, which ties into a question, have you looked at kind of thermal load reduction and innovative processing technologies? Because I think, yeah, one question kind of answers the other, and then we'll kind of end the Q&A there.
Yeah, very quickly, we talk about electrification and then some of the fuel switching, but in the very beginning, I presented the 5 pillars of decarbonization. At the end, to get to net zero, we need to follow all of that. Although not everything, like as I said, for example, you don't want to go to natural gas or biomass, you need to be careful. CCS is irrelevant. But energy efficiency, absolutely. As the more you reduce your energy demand, the fuel demand, the heat demand, then your size of heat pump is going to be, your electric boiler is going to be smaller. You save cost there. The amount of electricity and RE you need is going to be lower, significantly help with the supply side. So yes, but again, we can't lie to ourselves. We are talking about major adoption of decarbonization technology. We are not interested in a niche application of a niche technology here and there. I'm talking about getting the entire textile industry in China, entire textile industry in India, entire textile industry in Vietnam, and all other countries towards net zero, deep decarbonization, hopefully by 2050. Yes, energy efficiency here and there is going to help, but honestly, as someone who has worked 20 years on textile industry decarbonization and across different sectors, for textile industry to get to net zero, I can tell you 70 to 80% is going to come from electrification of heating tied to renewable. and maybe around 20%, 30% from other solutions, some energy efficiency here, a little sustainable biomass there.
Fantastic. Thank you both. So as the presentation and the Q&A has showed, there is a lot of work to be done on achieving this. It's, by no means inevitable and just going to happen in and of itself. So I'd like to take you through kind of AII's call to action and also how we aim to support the sector in achieving this. So we are at a critical juncture. Not only is it 2025, which is a kind of critical time point in and of itself, as we're halfway to that 2030 target, but to Ali's point, you cannot achieve net zero without looking at your energy source, and this will make up the majority of energy reductions that have to take place. And while, the kind of transition might not be immediate, there is immediate action needed in order to realize this transition. And a lot of that will come from brand leadership. We want to encourage a market signal to come from brands that they will, be pursuing this within their supply chains, that they will do policy advocacy in the countries that they source from, to kind of support the enabling environment we need in order to have sufficient corporate procurement of renewable electricity, and of course to collaborate with their suppliers so that the suppliers can implement this transition. And really importantly is that it should be a just transition. Ali and Cecilia presented the recommendations that are made in the report. It is very clear that this has to be a collaboration and there has to be financial support from brands to suppliers in order to make this happen. Those payback periods mentioned are quite a lot longer than the sector currently feels comfortable with and what currently takes place. So there will need to be financial support in order to bring that ROI to a level that textile manufacturers can accept and can implement. And being clear on what brand decarbonization priorities are, a transparency around that on how this links to sourcing strategies is essential to have that collective effort, so that brands, textile manufacturers, policymakers, financial institutions, and utilities all kind of work together on this topic. So what is AII aiming to do about this? We will have a climate solutions focus. For those of you maybe not so familiar with AII, we have a climate solutions portfolio, which is a kind of a list of vetted solutions. And to the last question that was asked, we will have a big focus on solutions that reduce that thermal load. This is not only relevant for countries which may be electrifying at a later stage, but for textile manufacturers across the board that are hoping to improve the kind of economics of electrification. The first step is really to reduce the amount of energy you're using in the first place. We have a program called the Renewable Energy Transition Initiative, which helps textile manufacturers with that technical assessment of how do I set up such an energy system, helps with the vendor selection as well as the implementation. This is something that we're launching in China this year, and we'll be piloting in India and Vietnam as well. And we offer grant funding as well. So actually, we had a call for grants that was opened in November for suppliers to come with electrification projects that we could provide the grant funding for those pilots. And that deliberation is actually currently underway. And I look forward to sharing with you in a couple of weeks' times which projects that we supported. Then we will also do a lot to kind of bring the ecosystem around this topic. So we are launching a supplier or setting up a supplier advisory council this year, meaning that we want to make sure that this transition is a just one. And in order to do that, we want to hear from suppliers, of course, what is needed in order for the sector to achieve a just transition and how that can filter into AII's work to make sure that all of the support we do give is supporting suppliers in the way that they need it. As I said earlier, we really want to encourage a brand electrification market signal, renewable energy procurement targets, so that their sourcing strategies are very much aligned to net zero and that this is communicated to the textile manufacturers within their supply chain. And finally, making sure there's sufficient financial tools to support this. We've discussed a lot that, you know, there is a price tag to this, and there is a lot of sustainable finance work that AII is currently doing and will continue and increase to do to make sure those different tools are available for textile manufacturers, for brands to use to support their implementation. And this links into wider industry collaboration work that AII does as well. Some of you may be familiar with the carbon and energy intensity benchmark that we're working on. This is our aim to kind of create a core long-term business case for decarbonization, with sourcing teams linking this benchmark, creating that connection between the sourcing and sustainability teams, with the carbon intensity benchmark really being the one to track, you know, where is your supply chain on its low carbon thermal energy transition. We are exploring which role AII might play in renewable electricity. It is the core part of making electrification happen, and that corporate procurement is available in the country studied, but is there a role that AII has to play in kind of the collective action around that? So that's something we're actively exploring. And this links into our industry decarbonization roadmap work with Cascale as well, where we are engaging the top 1,500 emitters in Hague FEM to embark on this journey. And finally, we are hosting one event so far this year, which is a local activation in India, where we're engaging some of the key textile manufacturers that we work with, that our brands work with, to discuss this topic and really figure out, you know, how can we collectively implement. And then there's also the Cascale Forum in Vietnam in a couple of months' time, for which the QR code is here, where we will also be discussing this topic among some of the other collaborations with Cascale that I have mentioned. So that was a whistle-stop tour in what we will be doing on this topic. And I do encourage you to kind of reach out if you have any interest in our support. Please do reach out to us. And of course, you know, the report is on our website. This recording will be shared, the slides will be shared, and it's impossible to really do the report justice in such a short amount of time. It's a lot of pages of really great analysis. So we thank you so much for joining today, and I hope that the questions that went unanswered in the webinar can be answered when you read the report. So thank you so much to GEI and to everyone who has attended.
Thanks, everyone.
Great. Thank you. Bye-bye.